Hello everyone, my name is P. Abdul Khader Jilan, studying 8th SEM ISC from Sri Venkateshwara College of Engineering. Today I am here to present my technical seminar on IoT-based non-intrusive automated driver drowsiness monitoring framework for logistics and public transport applications to enhance road safety, under the guidance of Dr. Shalini V, Assistant Professor, Department of ISC. The contents are introduction, related background, objectives, working or implementation, future enhancement, conclusion, and references. Moving on to the introduction, driver drowsiness is a major safety concern in logistics and public transport applications. Long working hours and driving conditions can lead to fatigue and a decline in driver alertness, increasing the risk of accidents on the road. Therefore, there is a need for effective driver drowsiness monitoring systems to improve road safety. In recent years, the Internet of Things IoT has emerged as a promising technology for creating non-intrusive automated driver drowsiness monitoring frameworks. IoT devices can be used to collect data on a driver's behavior and psychological indicators in real time, which can be analyzed using machine learning algorithms to determine whether the driver is at risk of falling asleep at the wheel. This technology has the potential to significantly enhance road safety in logistics and public transport applications. Here we will explore the key features of the proposed system, including the types of sensors and IoT devices used to collect data, the machine learning algorithms used to analyze the data, and the real-time alerts that can be provided to drivers and fleet management teams when drowsiness is detected. We will also discuss the potential benefits of this system, including the improved road safety, reduced accidents, and increased efficiency in logistics and public transport operations. Overall, an IoT-based non-intrusive automated driver drowsiness monitoring framework has the potential to significantly enhance road safety in logistics and public transport applications. It can also help reduce the economic cost associated with road accidents and improve the overall quality of life for drivers, passengers, and other road users. Now moving on to the related background, several approaches have been proposed that can be broadly categorized as follows: thresholding based approaches, traditional machine learning based approaches, and the deep learning based approaches. The first approach, that is thresholding based techniques, tells that a threshold based model relying on image processing was proposed by using a smartphone camera, which used eye openness, mouth openness, head pitch angle, and head yaw angle as parameters. It used data from the mobile camera and GPS. However, the limitation of this method was highly battery consumption due to the use of a live camera feed for a long time. The second approach, that is the traditional machine learning based techniques, reveals that it makes use of the HAA or cascade algorithm for face detection and the images are taken from a camera. The third approach, that is deep learning based techniques, reveals that the system detects facial features from images and delivers them to the trained model to identify the state of drowsiness on an Android application. Actually, driver drowsiness is a significant factor that can contribute to road accidents. In logistics and public transport applications, drivers may spend long hours on the road, which can increase the risk of drowsiness. Therefore, there is a need for an automated driver drowsiness monitoring framework to enhance road safety. The Internet of Things has the potential to provide a non-intrusive way to monitor driver drowsiness. IoT devices such as sensors and cameras can be used to collect data on driver behavior, such as eye movements, head position, and steering wheel movements. This data can be analyzed to detect signs of drowsiness, such as slow eye movements, drooping eyelids, and changes in steering wheel movements. Automated driver drowsiness monitoring frameworks have been developed using machine learning algorithms that can analyze the data collected from IoT devices to detect signs of drowsiness. These frameworks can then alert the driver or send notifications to the logistics or public transport company to take action, such as scheduling a rest break or replacing the driver. Studies have shown that automated driver drowsiness monitoring frameworks can significantly reduce the risk of accidents caused by driver drowsiness. They can also improve driver performance and reduce fatigue, which can have a positive impact on the overall safety and efficiency of logistics and public transport operations. The development of an IoT-based non-intrusive automated driver drowsiness monitoring framework applications has the potential to enhance the road safety and improve the efficiency of these operations. Coming to the objectives, the main objectives of the IoT-based non-intrusive automated driver drowsiness monitoring framework are to develop an IoT-based non-intrusive automated driver drowsiness monitoring framework that can accurately detect driver drowsiness in real time and provide timely alerts to prevent accidents in logistics and public transport applications. To evaluate the effectiveness of the developed framework in real-world situations through field trials. To address the challenges associated with developing and implementing such a framework, including defining machine learning algorithms, addressing privacy concerns, ensuring cost effectiveness, and addressing legal and regulatory requirements. To enhance road safety in logistics and public transport applications by reducing the incidence of driver drowsiness related accidents. To provide a cost-effective and easy-to-use solutions for logistics and public transport companies to monitor driver drowsiness, potentially reducing insurance costs and improving operational efficiency. Overall, the study aims to develop and implement an effective IoT-based non-intrusive automated driver drowsiness monitoring framework that can enhance road safety in logistics and public transport applications while addressing the challenges associated with developing and implementing such a system. Coming to working and implementation, the proposed methodology for an IoT-based non-intrusive automated driver drowsiness monitoring framework can be divided into several steps: system design, sensor selection, data collection, data processing, drowsiness detection, alert generation, continuous monitoring. Coming to the system design, the first step is to design the overall system architecture, which includes selecting appropriate hardware and software components for the IoT devices, sensors, and communication protocols. Sensor selection. The second step is to select appropriate sensors that can detect driver drowsiness accurately. These sensors can include facial recognition cameras, eye tracking cameras, and physiological sensors such as heart rate monitors. Data collection. The selected sensors will collect data continuously during the driver's journey. This data is then transmitted to the cloud using IoT communication protocols. Data processing. The collected data is then processed in the cloud using machine learning algorithms to detect driver drowsiness accurately. The algorithms can include image processing and computer vision techniques for analyzing facial expressions and eye movements, as well as signal processing for analyzing physiological data. Drowsiness detection. Once the machine learning algorithms detect driver drowsiness, the system can send an alert to the driver, the logistics manager, or the transport authority. Alert generation. Alerts can be generated through various means, including audio and visual alerts in the vehicle, or through a mobile application. The logistic managers or transport authority can also receive alerts in real time, allowing them to take necessary actions to prevent accidents. Continuous monitoring. The system will continuously monitor the driver's drowsiness throughout the journey, ensuring that the driver remains alert and focused. This slide shows the layered architecture of the proposed system. Broadly, the system consists of four major blocks, namely embedded system, edge computing, cloud computing, user interface. Embedded system consists of sensor layer, and it consists of camera, buzzer, push button, and embedded board. Sensor consists of RGB camera, sound sensor, Raspberry Pi 4, Jets and Nano. Coming to the edge computing, it consists of two layers, processing layers and pre-processing layers. Processing layer consists of facial landmark detection, eyes, mouth aspect ratio, ear to nose Euclidean distance, thresholding trigger alert, establishing an internet connection. Pre-processing layer consists of RGB to grayscale, ROE detection. Coming to the cloud computing, it consists of two layers, storage layer, network layer. Storage layer consists of authentication, real-time database, and storage. Network layer is Wi-Fi. Coming to the user interface, it consists of application layer. Here, application layer consists of authentication, driver status, drowsiness detection. Here, the embedded systems block consists of a sensor layer that contains an embedded board, an RGB camera, a buzzer, and a push button. As for the choice of embedded board to demonstrate the effectiveness of the proposed framework, we here tested with Raspberry Pi and Jetson Nano, which are commercially off-shelf open source boards and commonly used in related applications. The framework is, however, flexible to the use of other embedded boards as well. Raspberry Pi has an onboard BCM43438 Wi-Fi Bluetooth combo kit. It supports 2.4 GHz 802.1 in wireless communication. Jetson Nano has a Wi-Fi card based on an Intel 8265AC chip and LAN port that acts as a gateway for internet connectivity and allows wireless communication for data streaming to a cloud database. Moreover, the USB camera, buzzer and push button can be connected via GPIO pins and USB port respectively. Here, Jetson Nano gives much better computational performance for computer vision related applications. This slide shows the user interface. The user interface consists of the application layer that provides an interactive interface on a mobile application for both the driver and admin. They can register themselves, sign in, and access required the functionalities such as driver status, drowsiness status, alert notifications, and real-time location. The Firebase real-time database is connected and synchronized with all the edge nodes that provide real-time data for multiple drivers. The Android application plays a significant role in the Internet of Things based driver monitoring systems. A unified application allows both the driver and admin to register into an application as shown in figure 1. At the time of registration, the data is stored on Firebase database, and by using the same credentials, drivers and admin can sign into the applications to perform their respective functionalities. The driver can start or stop a ride, select a route, and activate or deactivate their location for real-time location, as shown in figure 2. The location feature is implemented by using background services. Even if a driver exits the Android application, still location services runs in the background and keeps updating location coordinates on the cloud database after every 4 seconds as shown in figure 3 for real-time location tracking by the admin. After adding a driver, the admin can visualize the real-time status of drowsy drivers along with the other details on the main screen as shown in figure 2. Moreover, automated driver evaluation is implemented by assigning drowsiness points along with drowsy images as evidence, where the admin can check previous drowsiness status for driver's evaluation. This slide tells about the alert system. The alert mechanism is categorized into onboard alert and remote mobile notification alert, where onboard alert triggers when any one of the three of facial actions, eyes closed, yawning and distraction are detected as abnormal to get the driver's attention back to avoid an accident. If a driver falls asleep, an alert notification is received on the admin mobile application along with the driver's drowsiness images, timestamp and location for tracking. We tested the alert system for all three scenarios on different subjects and acquired a 100% success rate for both onboard and mobile application. Moving on to the future enhancement, in integration with other vehicle safety systems. The driver drowsiness monitoring system could be integrated with other safety systems in the vehicle, such as lane departure warning, forward collision warning, and automatic emergency braking, to provide a more comprehensive safety location. Personalization of the system. The system could be personalized to each driver's unique characteristics, such as their driving habits, physical characteristics, and sleep patterns, to improve the accuracy of the drowsiness detection. Real-time monitoring and feedback. The system could provide real-time feedback to the driver, such as an audible alert or vibration, to alert them to their drowsiness and prompt them to take action to prevent a potential accident. Cloud-based analytics. The system could leverage cloud-based analytics to provide insights into driver behavior and fatigue patterns, which could be used to identify potential safety risks and inform driver training programs. Integration with mobile devices. The system could be integrated with mobile devices such as smartphones or smartwatches to provide drivers with additional feedback and alerts when they are outside of the vehicle. Multi-modal sensing. The system could incorporate additional sensing modalities such as heart rate monitoring or eye tracking to improve the accuracy of drowsiness detection. Predictive analytics. The system could leverage predictive analytics to anticipate when a driver is likely to become drowsy based on factors such as time of day, length of shift, and driving conditions, and provide proactive alerts to prevent accidents. Advanced machine learning algorithms. The system could use advanced machine learning algorithms such as deep learning to improve the accuracy of the drowsiness detection and reduce false alarms. Moving to the conclusion, the framework uses various sensors and machine learning algorithms to detect driver drowsiness and alert the driver or the fleet manager. Overall, the paper provides a well-structured and detailed explanation of the proposed framework, including its architecture, hardware and software components, and data processing techniques. The authors also present the results of their experiments, which show the effectiveness of the framework in detecting driver drowsiness. The proposed framework has several benefits, including enhancing road safety, reducing accidents and fatalities, improving driver performance and productivity, and reducing potential costs for logistics and public transport companies. However, there are some limitations that need to be addressed in future research. For example, the framework relies on accurate and reliable data from various sensors, which may be affected by environmental factors such as lighting conditions, weather, and road conditions. The authors also do not consider the potential ethical and privacy concerns that may arise from monitoring drivers' behavior. In conclusion, the paper presents a promising framework for automated driver drowsiness monitoring, which may the potential to improve road safety and driver performance in logistics and public transport applications. However, further research is needed to address some of the limitations and potential ethical concerns associated. Coming to the references, these are the reference papers which I have researched for my seminar topic. That's it. Thank you for your kind attention.